Hello, Amiga coders. This is Photon of ScoopX again, continuing to the fifth part of the demo tutorial, or I should say Amiga Hardware Programming tutorial. So, this here is our, as yet, tiny little program, and what we want to do is to change this wonderful piece of code to have its own display, if not screen buffer yet. So to achieve this, first I want to change this back. I just changed the color below the line to be the same as the one we set above the line. As you can hear, I'm rather tired. I have to apologize for my voice for all these tutorials. So how do we do this? How do we turn off? How do we get our own display? Well, the Amiga has a custom chip called the copper, or which is a sort of a coprocessor, hence its name. You can wait, you can move, you have conditional branching, and a few small tidbits, and with the copper you can poke all the other custom chip registers. So how do we use this copper? Well, first of all, we create a copper list, and this is a simple data declaration. We'll make a label, and we're going to first of all change register DFF100, which, if you look in the available hardware documentation, is the bitplane control register. However, in the copper, the registers start at the custom base, so-called custom base, which is hex DFF 000, which means we don't need this. And this is the bitplane enable register, and we will normally, if you want to disable all bitplanes, then you clear all the bits in the bitplane enable register. However, there's a color burst bit which stems from the Amiga 1000 that needs to be set in order for it to be compatible with all Amigas. And well, basically that's it. That's the smallest copper list you can make. Now, to end the copper list, you add a wait. I can demonstrate a wait command. For example, this copper list command waits for scanline hex ASCII, horizontal position 1. 7 is better for the start of the line. And this is the mask. You can have a loop that repeats in the copper, and then you can change this mask to match every 16th line or every 8th line or some such thing. And there goes the mic. And you can get these blinds effects that you can see in some demos. Either way, this is the mask. This is the default mask. That means mask the last bit so that you trick the copper into making it believe it's a proper wait instruction. And apart from that, mask no bits. So this definitely waits for raster line hex ASCII. Now, to modify this, we can modify this to tell the copper that there are no more instructions this frame. We do this by putting in an impossible wait position with a horizontal position of that much and a vertical position of that much. That's detected by the copper as the official end of the copper list. So that's it. So that's our copper list. The only thing it does is set the number of bit planes to be displayed to 0. Later we will add bit plane pointers to this copper list, but for now this copper list is complete. Now an important thing is to know that copper lists, samples, and graphics to be used by the blitter, etc., anything that's supposed to be used by the custom chips, must reside in chip memory. By default, our program ends up in whatever memory we allocated when we started ASM1, which, if you recall, was 200 kilobytes of fast memory. So that means this code will run in fast memory, but the copper must not run in fast memory. To fix this, we add a section statement. That means we must name the demo or something. Let's call it tutorial. And we want to declare what type of stuff is in this. There's code, there's data, and there's BSS. There are some others, but these are the only ones you have to be concerned about for the most part. Now, specifying that it's code or data doesn't matter in this case. I will declare it as data since it's data. And following this code, data, or BSS hunk tag, as they're called, there follows an underscore, and then either, well, if you omit the underscore C in this case for chip memory, or the underscore F for fast memory, or the underscore P memory, public memory is assumed. That means it will first grab fast memory if available, else chip memory. In this case, we must tell the assembler to put this piece of data in another hunk, please. A hunk that will end up in chip memory, so that this label signifies an address in chip memory. We can test this by commenting this out and printing the value of the copper address. As you can see, it's way up in fast memory. I see that because the address is above hex, what is it? Something like that. So to move this to chip memory, we add the section statement, and it's very low down in the chip memory. There was some small pocket of unallocated memory there that this little copper list could fit into. So now we need to set our copper. If we set the copper before we turn on the interrupts, the operating system might interfere and set its own copper list to this copper list or the other one there. And so we must put it in the init part of the program, but after disabling the interrupts. Now, normally you would do this after waiting for the next frame. However, if you set it after you disable the interrupts, then it will take effect the next frame. This is the hardware checking the copper pointer once every vertical blank. So to do this, we move the literal value of the copper address to this custom chip register. This is the copper pointer register, and as you can see, this is different from all the other moves we've done so far to custom chip registers. This one is a long word move because the address is a long word address. All addresses on Amiga are 32-bit. Some machines are limited to a 24-bit address bus, but that's basically none of your concern. It's nothing you need to worry about. All the memory that you can access is within the address space of the Amiga you're using. So this sets the copper, but as usual, as with the interrupts, if we run this, it will change the copper to our copper, thus changing which the copper list is what renders the display, basically. Not quite, but it's a display list if you're familiar with those. Basically, it tells Denise, the chip that's responsible for drawing the pixels, sending the pixels to the monitor or TV, what the display looks like, how big it is, where the pixel data is, and so on. You absolutely do not need a copper to do this. We could achieve the same thing by poking the bitplane enable register at the start of each frame. But, well, you can do that exercise if you want, if you doubt my veracity. But the important thing here is to save away the original copper pointer, the one you're looking at right now, the one at the display list that tells Denise what operating system screens to display. So we can't do this. We cannot do this after we turn off the system, because we need the system to fetch the address. Specifically, we need to open graphics library, save away the current copper list address, and restore it at the end of restore it at exit. So where does the system get turned off? It gets turned off on this line. When this line is executed, the system is no longer available for library calls. So I like to put all the library stuff at the start, because then everything that follows is my code. To open any library, what you do is you type this magical harangue. This is the exec base. This is a permanently open library whose base pointer is always in address 4 in memory. Notice how I didn't use the literal sign here, because we don't want to move the number 4 into A6. We want to move the contents of this address in A6. So by omitting the literal, we are reading a value for memory. Next, we need to clear D0, which is a version number. And furthermore, we need to tell it which library to open, and we do this by giving it an address that we're giving it a pointer in an address register that points to an ASCII text, which is the name of the library. Here we use the literal because just as we set the copper pointer here, we want to move the name pointer into A1. Let's declare this name, and this will teach you something new. Between pieces of code, subroutines, etc., you can put any data you like. For example, here we have the graphics name, and we now declare a string, and we terminate it with a 0 byte. Sorry, this is called ASCII 0 notation. So simply name, and you add a 0 at the end to tell it that that's the end of the string. Now that we've set up the registers for the library call in ASCII library, let's call it. How do you call a library function with a jump to subroutine? I happen to know that the offset from ASCII base to the function called old open library is -408. So this is a bit special. We are adding an offset to a base pointer and jumping to it, saving the return address on the stack. I'll return to that later. Anyway, this is the method to use to call a library function. In this case, A6, which is always the library pointer, library base pointer, is ASCII library. We give it some parameters and call the old open library function. Now what we get back is a base pointer to the graphics library. We've just opened the graphics library. We need to do this to get the base pointer. And values are always returned in D0, data register 0. So how do we use this? Well, we need to put it in a pointer an address register first of all, because we need to look up, fetch data from the copper pointer from an offset from this address register. So you move the return value to an address register to use it as a pointer, and then you fetch the current copper pointer. I'll have to look that up, but I think it's correct. Because there are two copper pointers, I wanted to oversimplify it this far. Could be another address, we'll test that. And we want to save this away, so we save it in data register 4, let's say. So this is the original copper pointer. Now we're done. If we should be proper, we should close the graphics library, because when you open a library it steals a few hundred bytes of memory. So let's go ahead and do that, and luckily we've put it in the right address register already. The close library function wants a library address in address register 1, and of course it needs the library base in A6. Now this function is not in graphics library. You can't close graphics library with a graphics library function. you do it just like you did with old Open Library. You call a function in exec base. So all we have to do here is call the close library function. So now we have the original copper pointer in D4. And we turn off the system and we set our own copper, and at exit we restore the copper pointer address. Should we do this before or after restoring the system? Well, I think hardware access should be done while interrupts are turned off. So we'll go ahead and do this here. And I will, after I set the copper pointer, I will turn on the interrupts again, and the copper list will switch back at the next vertical blank interval, at the next frame. And of course I was wrong, this was all unrehearsed, so this is naturally the correct address to use. The address 50 was for the secondary copper list. You can use these two copper pointers to have two copper lists running, one initializing copper list and one that you switch to. So 38 it is, and as you can see, U stands for update, by the way, as you should be able to read on the screen. Now not only does the original screen restore properly, but we also get our mouse pointer, and it doesn't hang if you move this around as it did before. Sorry about that. See you in the next tutorial.